Hello, everybody. Welcome to another session of our QuantEP seminar, Quantum Computation and High Energy Physics. It's a great pleasure to welcome today Patrick Hayden from the University of Stanford. It's a great pleasure to have you and see you again. Thanks also everybody for joining. So Patrick Hayden has been a leading scientist in quantum information theory, quantum computation, and also one of the first to explore the connection between quantum information and quantum computation and black holes and the physics of information at that level, and also the role of entanglement there, with many interesting and pioneering contributions on this front, as well as on others in quantum computation and quantum information. So it's really a great pleasure to have you today with us, Patrick, and telling us more about this fascinating direction. Thank you very much for joining.
All right, thank you for that kind introduction and for the invitation to speak today. I'll be using my tablet to present, and so I'll begin by sharing my screen. I'm going to be speaking about what is by now in some ways an old topic in this subject, which is the role of entanglement in holographic theories of quantum gravity. And I'm going to be telling you about a quantity called the reflected entropy. And so coming from the world of quantum information and having wandered into quantum gravity, I was used to bringing with me all kinds of measures of correlation and concepts like quantum error correction, and then applying those to the study of quantum gravity. But this is a situation in which people working in quantum gravity identified a quantity that in quantum information we had never bothered to, or we had never had the idea to think about before. This is this reflected entropy, and I'll eventually tell you what it is. And it's a very interesting quantity, partly because it has a very nice geometric interpretation in holography, but it is also connected to multi-particle entanglement. It's relatively easy to evaluate. And so it has many wonderful properties and also mysteries associated to it. And so I'll tell you a little bit about those mysteries. I'll introduce what it is, and hopefully we'll get to someplace interesting after about 45 minutes or so. The talk will be based on a paper called The Markov Gap for Geometric Reflected Entropy by myself, Onkar Parikar, and John Source. Onkar was a postdoc at Stanford. John is my PhD student who will be graduating this year. So reflected entropy, why would we want to think about it? What is it? So let's just think about the why first. Probably about, I guess, almost 20 years ago now, Ryu and Takeyanagi proposed a formula for calculating the entropy of a subregion of a quantum field theory with a holographic dual in the context of the ADS-CFT correspondence. And so I'll tell you, you've probably seen this formula before. I'll review it in a little bit, but this was a way of evaluating the entanglement entropy, the von Neumann entropy for a mixed state in one of these theories by relating it to a purely, to a geometric quantity. And at first that just seemed like, okay, well, it's a way to calculate some entropy, but the consequences that flowed from that formula over the subsequent 15, 20 years were really quite remarkable. I'm not going to give you an exhaustive list, but one of them was this result entanglement wedge reconstruction, which basically asked the question, if you had, again, in the ADS-CFT correspondence, so this is supposed to represent the spatial slice of a spacetime, which is asymptotically anti-de Sitter. On the boundary, there's a conformal field theory. They're supposed to be dual to each other. And you could ask the basic question, if there's a local observable O inside that bulk, how do I express it as an observable in the boundary theory? And entanglement wedge reconstruction basically tells you when you can do it, where you can do it, what kinds of observables on the boundary are necessary. And it's all through the formalism of quantum error correction. And that flowed from this Ryu-Takeyanagi formula. Now, the Ryu-Takeyanagi formula was originally for static spacetimes, and so it was eventually generalized to a covariant formula for general spacetimes. And even to the situation in which you would have large amounts, not just of kind of geometrical entanglement, but also large amounts of entanglement in the quantum fields living in the spacetime. That's what's called the quantum extremal surface formula. Back in 2019, which is not that long ago, combining these elements, it finally became possible to correctly calculate the entropy of Hawking radiation evaporating from a black hole in the context of ADS CFT, and then that was generalized to black holes evaporating in flat spacetimes, which is not quite our universe, but it's pretty close. And so this really now gives we know why Hawking was wrong, right? This is the debate that was going on for 40 odd years about the nature of radiation in the black hole evaporation process. And there are still there's still questions about that, the detailed microscopic mechanism, because this calculation is done semi-classically. But I'd say that this was a huge success to finally be able to resolve this question and do the calculation properly. And so there's a lot of mileage to be gained by studying correlation measures in holographic theories of quantum gravity. And if you accept that premise, we could ask the question, what kinds of correlation measures have simple and compelling bulk interpretations? Also, the von Neumann entropy, if you prefer the entanglement entropy, is a measure of correlation in pure states. And it has nothing at all to say about multiparticle entanglement, multipartite entanglement, the entanglement structure, or the entanglement between more than two regions of spacetime. And in the context of quantum information theory, multipartite entanglement has a bit of a checkered past. There was a large flurry of interest in multipartite entanglement back in the late 90s, but it turns out it's a very complicated subject, and it doesn't simplify in the same way that single particle or bipartite entanglement does. And so to some degree, people stopped thinking about it because they couldn't really make sense of it in the way that they would like to. But one of the things we're going to do today is we're going to see that this reflected entropy does tell us something interesting about multipartite entanglement. And in fact, it's going to connect multipartite entanglement to specific geometrical structures in the holographic spacetime. And so that's going to be the end point of our discussion. But a good portion of the talk is just going to be pedagogical, introducing this reflected entropy. So let's do that now. The reflected entropy, to define it, we have to introduce the notion of a canonical purification of a mixed quantum state. So if we're given a density operator, rho, that density operator is a matrix, right? And we often write the matrix as a sum of kets and bras. And so it's an element of the Hilbert space of the theory, tensored with the dual of the Hilbert space, right? The kets and the bras. And if we like, we can treat the space of operators, H tensor H dual, as a Hilbert space itself, and endow it with an inner product. And so the inner product that we'll use is just going to be, I'll write it this way, I'll use double angle brackets just to distinguish it from the usual Hilbert space inner product. But the inner product between a rho and a sigma will be the Hilbert-Schmidt inner product, the trace of rho dagger sigma. And of course, density operators are Hermitian, so the dagger doesn't do anything, but you could extend this to non-Hermitian operators. And a very simple observation is that if you use this inner product, the quantum state associated with the square root of rho, remember rho is a positive semi-definite operator, so it has a well-defined unique positive semi-definite square root. And that's a normalized quantum state, because according to this inner product, the way we should take the inner product is the trace of the square root of rho times square root of rho, which is the trace of rho, and density operators have unit trace. And so square root of rho with respect to this inner product is a normalized state. And so that will be our purification, canonical purification of the density operator. So why is it a purification? Well, there's a lot of symbols here, but what I want to say is that we've purified from the original Hilbert space to the Hilbert space tensored with its dual. And so the density operator is going to have two copies of H tensor H dual, right? Because you have to take the purified pure state and the bra associated with that purified state. And so I've written subscripts L and R here to indicate the left side and the right side, but these are all the same Hilbert space. If we want to see whether square root of rho is a purification of rho, what we should do is trace over the second copy. And the second copy here corresponds to HL star tensor H right. And if you do that little calculation, I'm not going to do it here, what you're going to find is that you get exactly rho back. And so it is a purification. It's canonical because we didn't have to make any choice of basis here, right? A very similar thing that you could do that might be a bit more familiar to quantum information theorists is you could just say, well, act with the square root of rho on half of a maximally entangled state, unnormalized. And what you would get then is a pure state such that if you trace over the ancillary system, you get back rho. But the choice of maximally entangled state generally requires a choice of basis. But if you choose a maximally entangled state in H tensor H star, which is actually just the identity operator, you don't need to choose a basis. So that's why it's called the canonical purification. And with the canonical purification in hand, we can define the reflected entropy. It's a measure of correlation. I'm going to put an asterisk on that and come back to it at the very end of the talk. But we're going to be given now a bipartite density operator, rho AB. It can be a mixed density operator. And I'll use this notation here. S, you have like entropy, R for reflected. Reflected entropy between A and B for rho is equal to the entanglement entropy of the canonical purification, like that. So remember that in the canonical purification of an A-B state, there are going to be Hilbert state spaces kind of labeled by A, B, A star, and B star. And so I'm looking at the entanglement in the canonical purification between the A star half of the state and the B star half of the state. And that's this definition of reflected entropy. So it's pure state from a mixed state, we generate a pure state, and then we look at the entanglement in the pure state. And here's notation that I deprecated, so square root of rho. Now, to get a feel for that, let's just look at some very simple examples to see how it behaves. So the simplest example to start with would just be perhaps a pure state. So we have a bipartite pure state, and we ask, well, how does this reflected entropy work out? Well, the density operator for that bipartite pure state, I've written it down here on the right. It has AB systems and A star, B star. And so notationally, my rho, I can put the double angle brackets on it, the double ket. There's my pure state. So what is the reflected entropy of this thing? I have to evaluate the A star entanglement entropy of this object. That object is a product across A and A star. And so I can just write it out. For a product state, the von Neumann entropy is the sum. So this is the entropy of A for psi plus the entropy of A star for bra psi, like that. And of course, these entropies are the same. And so this is actually just twice the entropy of A for that original quantum state psi. And I put a little exclamation mark here in the wrong place. Oops. I wanted to emphasize this factor of 2. And so you might have thought that if the state was already pure, when you purify it, there's nothing to do. And so you just get back the von Neumann entropy. But when in the canonical purification, there are 2 copies of the original state. And so you get twice the von Neumann entropy, the entanglement entropy of the original state. That's a little point to note. The other really simple example to think about is a product state. And so the product state, we'll call it rho AB. It's a product of sigma A with tau on B. What does the canonical purification for this look like? Well, we can purify sigma first, and we get a purification on A star, and then purify tau, and we get a purification on B star. But if we're going to evaluate the von Neumann entropy now on A star we have a pure state. And so the von Neumann entropy is 0. And so that seems to be pretty reasonable. If you're familiar with the mutual information of a mixed state rho, which is the entropy of rho on A plus the entropy of rho on B minus the joint entropy, these answers are actually exactly the same answers as you would get for the mutual information. Right, that the mutual information of a pure state is twice the von Neumann entropy of the reduced density operator. For a product state, it's exactly 0. And so it seems actually that this reflected entropy, even though it's just the entropy of a single state, is behaving very much like a mutual information. But it is not equal to the mutual information, as we'll see. But it does seem to be capturing some interesting notion of correlation in the joint state. And so now let's move on to the holographic interpretation. And I should point out that this reflected entropy was first defined in 2019 by Dutta and Faulkner, and they also identified this holographic interpretation of the reflected entropy. So first, let's just I'll go through the Ryuta-Kiyanagi formula again, in case some of you aren't familiar with that. And as I was saying at the beginning, this is a way of calculating an ADS-CFT, so a situation where you have a conformal field theory living on the boundary of an asymptotically ADS spacetime. And so in this picture, the circle should be a spatial boundary of basically the hyperbolic disk, or something that's asymptotically the hyperbolic disk. And we're going to choose some region in the boundary, which I'm calling A here, and we want to evaluate its von Neumann entropy. And the Ryuta-Kiyanagi formula tells you that to the leading order, again, I'm going to ignore some complications and just speak in this language for the period of the talk, ignoring bulk entanglement and higher order terms. That to calculate the von Neumann entropy, you minimize the area over some bulk surfaces, in this picture really bulk curves, that are related to the boundary in a certain way. And so let's call my bulk curves gamma, and I'm going to minimize over gammas, and they're supposed to be related to the boundary region A. And how are they related technically? Gamma should be homologous to A. And what does that mean? If you the term from topology, gamma union A should be the boundary of something. So that's the definition, that you put them together and they should be the boundary of something of one higher dimension. And we'll call the minimizer gamma sub A. Okay, so here you can see if I look at A and gamma sub A, there's a region in between them. And the region in between them, I'll call it WA for wedge of A, the entanglement wedge of A, is sitting in here. And gamma A union A is the boundary of the entanglement wedge. And so that's the definition of homology, and it also simultaneously defines this notion of entanglement wedge, which plays an important role in the theory of these things. So that's the Ryuta-Kiyanagi formula. And now let's use it to construct the holographic canonical purification. What you do is you start with the entanglement wedge of A. So that is basically, you have a portion of some region of the boundary, and then you have some piece of the bulk spacetime, but not the whole bulk spacetime, just this wedge part. And then you could take the CPT conjugate, basically the reflection of that piece of bulk spacetime. So now you'll have two pieces of bulk spacetime, and you glue them along gamma A, right? You glue them along the extremal surface. And so the picture looks something like this. So here I've introduced the time direction, which is perhaps a little bit confusing, but it helps you see the space-time. And so my interval A might be something like this. And it has a domain of dependence in the boundary. And so there's some, if I define the state on that interval, on that purple interval, then there's some region in the boundary on which that initial data can be used to solve the equations of motion, calculate all expectation values. And in relativistic theory, it basically forms a diamond. And then this pink region is the entanglement wedge inside the bulk. And I'm going to glue it along the extremal surface, along the minimal surface, to a reflection. And then that gives me some bulk construction, which is corresponds to the canonical purification. I guess something I should have said here, you can see that rho, if you like, you can assign rho to this spatial slice, or to an interval, say, in this spatial slice. But as I was saying before, because you can use the equations of motion to evolve forward and backward a little bit, it's more natural in the context of a quantum field theory to associate the state to a domain of dependence. And that's why we have these regions of space-time and not just regions of space. But from now on, for the rest of the talk, we're just going to look at spatial slices. So let's look, that's the construction. Let's see how it behaves in a situation where we have a bipartite density operator in the boundary. So now I'm again looking at a spatial slice, and I choose a region with two pieces. There's an A piece and a B piece, like that. And we're going to use the same prescription. We're going to take the entanglement wedge. The entanglement wedge of AB is this region in the middle. The extremal surface is the gamma. We'll take one of these, we'll take its reflection, and we'll glue along gamma. And so what does that look like? It looks like this. And so on the bottom, right here, I have one copy. On the top, I have the reflected copy. And I've glued, let's say, this gamma is here. And then this gamma is here. And so I have to glue to the matching extremal surfaces. And so in the right-hand picture, the lower gamma is glued to the very top gamma, like that. And that is the construction. And what you can see is, because I've performed these two identifications, on the right-hand side, I have a tube, right? I have a spatial cylinder. And so the canonical purification of this bipartite density operator rho AB, its bulk interpretation in quantum gravity is actually a wormhole, right? This tube is a spatial wormhole. Okay, so let's try to calculate the reflected entropy now. And I think I can drop these. Okay. So the prescription for calculating the reflected entropy is that we're supposed to go to the canonical purification over on the right here, and then just calculate and use the Ryu-Takanagi formula for AA star. Now, AA star is topologically a circle in the boundary, right? I start here, I follow that path, and I get back to where I began. And so it's a loop. And so I want to consider bulk surfaces that are homologous to AA star. And so those are basically going to be loops, right? Like this one here. I want to find the one of minimal area. And so the one of minimal area is sort of the one that's going to cut the narrowest cross section. And it's the length of this gamma AA star. On the right-hand side, on the left-hand side, well, yeah. So it's the length of gamma AA star. And because of the way that the canonical purification is constructed, this piece of gamma AA star is what in the left-hand picture I've called sigma AB. It is the curve which gives the narrowest cross-section of the entanglement wedge, right? It's where the entanglement wedge is narrowest. And so, and in the canonical purification, it appears twice. And so the reflected entropy is twice this, the length of this minimal cross-section of the entanglement wedge. And so there's an interesting point to make here, which is that the definition required us to talk about this canonical purification. But when we actually evaluate the reflected entropy, we find that it's something that we can calculate without looking at the canonical purification. We just look at the entanglement wedge of AB, and in the original space-time, and then we find the surface of minimal area, or the cross section of minimal area of the entanglement wedge. And so it's a property just of that you can calculate geometrically in the original space-time. And so that's an interesting simplification. Now, I should point out that this minimal cross-section quantity had been a subject of some interest prior to the introduction of the reflected entropy. And there are actually a number of candidates in the literature for what the area of this minimal cross-section should be. It was originally proposed that it would be the entanglement of purification, which I may come back to at the very end. Some of you may know what entanglement purification is, that would be related to the logarithmic negativity, the balanced partial entanglement. There were all these proposals. There were some heuristic arguments. But in the case of the reflected entropy, it's a calculation. And so this answer that the reflected entropy is actually twice the area of the minimal cross-section is on a kind of mathematical footing as rigorous as the Ryu-Takenagi formula was. And so we're very confident of this fact. All these other candidates are conjectural or potentially wrong. I'll just pause there for a moment and ask if anybody wants to ask any questions about the definition and the geometric interpretation of this quantity. No? All right. Well, what does this have to do with multipartite entanglement? I promised you at the beginning that we would say something about multipartite entanglement. We did see that the reflected entropy behaved quite a bit like a mutual information. And so let's think about the difference between the reflected entropy and the mutual information. And the mutual information, as I was saying before, is just entropy of the A subsystem plus entropy of B minus the joint entropy. The reflected entropy is the entropy of AA star in this canonical purification. So you can regard all of these entropies as being calculated with respect to the canonical purification, if you like. In the canonical purification, which is a pure state by construction, the entropy of B will always be the same as the entropy of its complement. So the entropy of A star, B star. And if you look at that quantity, with the 4 entropic terms there, that is exactly, by definition, what we call the conditional mutual information of A star with B given A. It is the quantity that the famous strong subadditivity inequality of quantum entropy tells us is non-negative. And so this simple calculation tells us that this quantity delta, which I'll call the Markov gap, is non-negative. And so the reflected entropy is always at least as big as the mutual information. And Akers and Rath in 2019 pointed out that delta, this Markov gap, actually detects multipartite entanglement. And what they observed was that if you have a pure state on a system ABC, so you start off with, say, a mixed state on AB, and then you purified it, or you start off with a tripartite system and only looked at the reduced density operator on AB, calculate the Markov gap delta, that if you only had bipartite entanglement in the original state on ABC, so some combination of bipartite entanglement, as I've kind of illustrated graphically here, you just do a little calculation and you find that delta has to be 0. And so if delta is non-zero, then you have to have multipartite entanglement in your tripartite quantum state. And in fact, you can say more. Last year, Zhu and al. Found the conditions for this Markov gap to be exactly 0. And it was that the pure state on ABC could be written as a linear combination of states that only had bipartite entanglement, as I've sketched below, in the right-hand picture. And so if delta is non-zero, then not only do you have multipartite entanglement, you have multipartite entanglement that cannot be expressed in this relatively simple form. Okay, so delta, which is an interesting quantity. Again, those of you in quantum information are probably familiar with the fact that when we try to write down measures of multipartite entanglement, we usually have to perform completely intractable optimizations, or it gets kind of messy. Here's a quantity which is really just it's just an entropy of some state, which is defined via an algorithmic process, a simple algorithmic process from the original density operator with no optimizations. And so this is an interesting property. And so now, I guess I just want to check the time here. Now we come to the work that I did with Onkar and John. We looked at what the holographic, or what the Markov gap means in holographic states. And our intuition for thinking about that comes from the theory of what are called universal recovery maps in quantum information, which was pioneered by Fuzzy and Renner in 2015. So they asked the question, suppose that you have some mixed state on a tripartite system, some general density operator rho ABC. So I've illustrated that with 3 legs coming in and 3 legs going out. It's an operator. Now, suppose we tried to make this general rho ABC by starting out with only rho AB and then acting by a quantum channel on B to produce BC, right? And so this is why we use the term Markov, because we're trying to make this tripartite correlation in a Markovian fashion. We're not allowed to touch A, but we want to act on B to produce the correct correlations in BC. So this is like a Markov process, a short little Markov process quantum mechanically. So can we make rho ABC in a Markovian fashion? And the conditional mutual information essentially controls how well you can do this. And so the result of Fuzzy and Renner can be expressed as saying the optimal fidelity, right? The mixed state fidelity, which is 1 if the states are the same, it's 0 if they're perfectly distinguishable. The optimal fidelity that you can achieve this way is bounded below by the exponential of the conditional mutual information. And so in particular, if the conditional mutual information is 0, e to the 0 is 1, and you can do this perfectly. And that was actually known previously. But so the interesting thing is that when the mutual information is now non-zero, but say it's small, then you'll be able to actually do reasonably well in this recovery process. Okay. So now recall that the Markov gap was a conditional mutual information, say for the canonical purification, A with B star given B. So let's try to apply that intuition of the recovery map to this canonical purification. So the procedure, if we look at this picture, we're supposed to start off with the AB state. So let's suppose we start off with the AB state. And holographically, in terms of the bulk, that means we have this region that I've highlighted in yellow. And what we want to make is the AB B star state. And in the bulk, the entire purple, that means we should be able to recover all the correlations of the entire purple region. That's the entanglement wedge of AB B star. How well could we do? Well, somebody who had access to B could, the B part of the AB state could just throw away the state entirely and then make the B star state. That's, in a Markov process, it's always an option to just throw everything away and start over again. You're not going to get the correlations with A correct, but you'll get the correlations between B and B star correct. Now, in a holographic, in the context just of quantum field theory, there's large amounts of entanglement at short distances. In fact, if you don't impose a cutoff, then there's an infinite amount of entanglement at short distances. And so in the bulk theory, the region, there should be entanglement across the regions that identified with squiggles here, right? Because there's, in the quantum, there's a space-time, and there's a quantum field theory living there. And locally in the quantum field theory, there's always a lot of entanglement. But if I started off with only the AB state, then the degrees of freedom that were entangled, say across this squiggly line, they didn't have their partners, right? There was entanglement, but you didn't have on the A star, but you didn't have the A star partner of that entanglement. So you just have some degrees of freedom that are noise. So that without access to this region of the bulk, there's no hope that you're going to be able to recover the entanglement across the squiggly edge. That was our intuition. And so the intuition then is that the Markov gap in this situation should be significant. It should be large. So let's check that. Well, here's what I just said. Or actually, let's consider another example, which actually illustrates a further feature of the situation, that the entanglement in the bulk should prevent us from performing this Markovian recovery. So here, I have a spatial slice which consists of a 3-boundary wormhole, right? So there's an A part, a B part, and a C part. And if I consider the density operator rho AB, and I want to calculate its von Neumann entropy, it turns out that the minimal surface is this gamma here. And that, for those of you who aren't too familiar with these things, this is an example where the homology condition is important, right? That I can't continuously deform gamma into these loops AB, right? But A, B, and gamma AB are the boundary of some region in the bulk. So the homology condition is acting here. If I look at the canonical purification, it's now a 4-boundary wormhole. And the squiggle region, that if I run through the same argument about trying to construct the A-B-B star entanglement in a Markovian fashion, the part that I don't expect to be able to make is this piece right here. Now, in this geometry, just by kind of varying my parameters a little bit, in this case, gamma is a compact surface, and I can actually make the size of gamma as small as I like, right? And so you might think in that case, well, if I can make this part this squiggly part as small as I like, the argument that I've just been making about not being able to properly capture the bulk entanglement goes away, right? That if the squiggly region with entanglement that I'm not able to reproduce in a Markovian fashion disappears, then I should be able to perform the recovery process. What we will find in our main result is that even if you shrink this squiggly region to 0, there will be some residual contribution to delta that never goes away. And that residual contribution to delta comes from a corner where the squiggly line intersects the entanglement wedge cross-section. I'll define that in more detail in a little bit. But the point being that a lower dimensional object, a corner, right, a higher codimension object in the bulk geometry provides an irreducible contribution to the Markov gap, and therefore the existence of one of these corners requires multipartite entanglement. Okay, so what is our result? More precisely, the Markov gap is bounded below by the curvature scale, which I've just been setting to 1 throughout, times logarithm of 2 over twice Newton's constant, times what comes here, the number of cross-section boundaries. Okay, so let's just do a little exercise now. We'll do some examples. So here I have, again, a system, if you like, I'll say the boundary is pure. I've broken the boundary into 3 pieces, A, B, and C. And I'm interested in the Markov gap for the reflected entropy for the AB mixed state. The entanglement wedge cross-section for AB is this region here. And as we saw before, its cross-section is this red piece, and the cross-section intersects the minimal surface in 2 places, right here and right there. And so the the number of components in the cross-section boundary is 2. And so in this particular example, the Markov gap is going to be bounded below by the curvature scale times the logarithm of 2 divided by Newton's constant. The 2 in the denominator cancels the 2 in the numerator. Let's do another one just for good measure. Here I have 2 intervals in the boundary that are actually touching each other. And so the entanglement wedge cross-section has 2 boundaries, but I'm only interested in the boundary that touches the minimal surface. And so that's this piece right here. And so the number of cross-section boundary components is 1. And so we could plug it into the formula again. And then let's look at the example that we were doing before with this pair of pants. The cross-section boundary for the AB region intersects the minimal surface in 2 places. So the number of cross-section boundaries is 2. Now, truth in advertising, I should say that we proved this only in the case of, well, I won't say only, but basically in the case of pure gravity, ADS3 cross CFT2. So this is not a hugely general statement, but one in which we could actually make progress. And I'm just going to quickly sketch how it works, and then we'll wrap up. So I'll illustrate the proof in this special case here, the one that we've been looking at for a while. We're going to want to calculate the Markov gap. Now, the Markov gap is the reflected entropy minus the mutual information, and the reflected entropy is twice this entanglement wedge cross section, right? That piece there. The mutual information, I should draw it in, has the length of gamma A. So there's gamma A. So we're going to subtract it. So it'll be a -1. We'll subtract the length of gamma B, the entropy of B. So that's gamma B. There's a -1. And then we will subtract negative the entropy of AB. So that means we're going to have a +1. So if we look at those pieces, in the middle we have a +1 and +2. On the sides we have -1s. We could repackage that sum as follows. We would take on the left-hand side this surface that I'll call KRT, kinked Ryuta Kiyanagi. We'll take the KRT of the A region and subtract RT of A. And that will give us all the right quantities for the left-hand side and 1 copy of the entanglement wedge cross-section. If we do the same thing for KRTB on the right, then we get the Markov gap. And so we're interested in these quantities. And to understand how they behave, we just need a little bit of hyperbolic geometry. And in particular, we need to know about right-angled hyperbolic pentagons. Now, in flat space, there's no such thing as a right-angled pentagon, but in hyperbolic space, there is such a thing as a right-angled pentagon, which all the sides meet at right angles, and the sides themselves are geodesics. And you can prove, without too much difficulty, that if you take 2 adjacent sides in a right-angled hyperbolic pentagon, I should say that in this geometry that I've drawn right here, the spatial slices are just hyperbolic space. So we take 2 sides A and B, and then a third side, which is the side opposite both of them that doesn't touch either one. Then there's a simple little inequality. The length of A plus the length of B minus the length of C is at least log 2. And so we're interested, because of the picture that I drew above, in the length of KRTA minus the length of RTA. So in this picture down below, we're interested in the length of the sum of the A's and B's minus the sum of the C's. Now, these don't look like pentagons. They in fact look, or say one of the regions here, I have right angles, a right angle, a right angle, a right angle, a right angle. And then I have this point going off to infinity. These look like quadrilaterals with these singular points at the ends. But in hyperbolic space, the boundary is infinitely long. And so these two curves going out to infinity, if you like, you could regard them as as hitting infinity at finite distances from each other. And so they both hit the boundary at right angles, and then there's a finite line segment between them, and it becomes a pentagon in hyperbolic space. And so this situation that I've drawn actually has each of these shapes has a degenerate side at infinity. So these really are, in terms of hyperbolic space, hyperbolic pentagons. And so the missing side is the one between A and C right here, between A and C. And so our inequality applies. And when we add these up, we have two hyperbolic pentagons. From each one of those, we get a log 2. And so the difference of the area of KRTA and RTA is twice log 2. If we go back to the Markov gap has one of these structures for A and another one for B. And so in the Markov gap, we'll actually have a 4 log 2. When we define the entropy, there's always a 4 Newton's constant in the denominator. And so what we find is that the Markov gap is bounded below by log 2 divided by Newton's constant. And that's the kind of argument that we make. To handle the general case of pure gravity ADS3 CFT2, a spatial slice is no longer the part of the hyperbolic plane, but it's a discrete quotient of the hyperbolic plane. And so we can work in the covering space of the hyperbolic of that space, which is then it is a hyperbolic plane. And we can prove that each of these KRT surfaces is homotopic to a smooth geodesic. So homotopic means can be smoothly deformed into a smooth geodesic. And the region between the original KRT surface and the smooth geodesic, just like in this picture, can be tiled by right-angled pentagons. So the inequality applies, and then the Ryu-Takinagi formula tells us that the area of the minimal surface will be less than or equal to the area of this geodesic, the length. And so that's how you handle the general case. And that's basically the story. The take-home message is that multipartite entanglement, witnessed by this non-zero Markov gap, is associated to codimension 3 structures in this space-time. So we already knew very well that codimension 2 structures, right, these minimal surfaces, were associated with bipartite entanglement and the pure state. And so now we see multipartite entanglement can be associated to these lower dimensional structures. How general that statement is, that remains to be seen, but I think it's interesting. What could we do next? Well, you could ask, does this generalize to higher dimensions? Does it generalize to having non-trivial matter inside the space-time? We did look at spherical matter perturbations and found that the result continued to seem to hold. I didn't tell you, but because we wanted to use the Ryu-Takinagi formula rather than its covariant variant in this argument, we were working always at points with a moment of time reflection symmetry. So can you do this more generally? But the thing that, as an information theorist, I'm most curious about is this reflected entropy. Throughout, I've been telling you it's a measure of correlation, and it behaves a lot like the mutual information. But the most interesting property, or the most basic property of mutual information, could perhaps be that it satisfies a monotonicity, right? The way that the reason we think of it as a measure of total correlation in the state is that if you look at a state with an A part and a BC part, that the correlation between A and B and C together is at least as big as the correlation between A and B, that monotonicity property. That is not known to hold for the reflected entropy. It's easy to show that holographically, but I will tell you it is a beast to try to show it, at least I found, to try to show it for general quantum states. I worked on this very hard with John for about 4 months, leading up until the holiday break before I finally decided it was time to set the problem aside. So it's very interesting, has a lot of structure, but we were not able to prove the monotonicity. If we could prove the monotonicity, it would actually allow us to evaluate the entanglement of purification, this other quantity that was conjectured to be equal to the length of the entanglement wedge cross-section. In fact, if monotonicity for the reflected entropy holds, then the entanglement of purification is equal to the length of the minimal cross-section. We already know that the reflected entropy is twice that length. And so monotonicity would be proving that the entanglement of purification is half the reflected entropy. And for those of you who don't know what entanglement of purification is, I can tell you in the questions, but I should be wrapping up. So the last thing I'll tell you is that if we could prove this monotonicity, the other reason I think it's very interesting is that we would essentially have a formula for the distillable entanglement in all holographic states. So distillable entanglement is basically how much useful entanglement you can get out of a mixed quantum state, as opposed to, for the purposes of things like teleportation, violating Bell inequalities, et cetera, et cetera. And that I think would be a quite interesting, powerful conclusion, all flowing from this innocuous looking inequality, but my confidence in the correctness of the inequality has been shaken by the fact that I tried to prove it for many months and was unsuccessful. On that note, I will thank you for your attention and ask you if you have any questions.
Thank you very much, Patrick. It's really fascinating work and results. Thanks a lot for sharing with us. And so we have some time for questions, so please just raise your hand or unmute yourself. So, okay, so I see Sugato. Hi, Sugato. Please,
Sugato, good to see you.
Hi, Patrick. Hi, Patrick. Very, very interesting talk. Yeah, I'm just wondering. So you are doing this, applying this to holographic states, but I guess you or others might have. Is it applied already to normal states, like the entropy, the difference one, like GHZ or W states, and is delta entanglement monotone, or what does it give for these kinds of states?
Yeah, well, excellent question. So the paper by Zhu et al. that I quoted, they numerically evaluated the reflected entropy, so the reflected entropy does, reflected entropy you can just evaluate, right? There's no optimization in it. So they looked at some many body systems. I don't remember exactly which ones, and some conformal field theories without holographic duals, and studied the behavior of the reflected entropy, and they compared it, and they numerically evaluated the entanglement of purification. So there are high energy theorists here. I didn't define the entanglement of purification. The reflected entropy, the way you get it is by choosing a very specific purification and then evaluating the entanglement entropy. The entanglement of purification, you optimize over all possible ways of purifying the state with no dimension bound a priori on the size of the system. So it's actually an infimum, it's not a minimum. And so it's a very poorly controlled optimization. Like in the history of quantum information, it's only been evaluated exactly for a very small, like 2 or 3 different states that are non-trivial. So, but they tried to numerically evaluate entanglement of purification. And in that paper, there's an entanglement of purification analog of the Markov gap. So they proved, canonical forms, if they proved the statement, if Markov gap is 0, the state has this particular form. And they also showed if entanglement of purification is 0, the state has some other, even more restricted form.
I see.
And then they evaluated them. But this question of monotonicity, there was not a lot done prior to our investigation. Dutta and Faulkner, when they first defined the reflected entropy, the interesting thing, it's pretty easy to prove the monotonicity statement for all the integer Renyi entropies. Right, so you think, oh, well, it holds for the integer Renyi entropies, it must hold for, but it's not, it's a hard thing. And so that's one of the reasons I believe it to be true. I mean, why would it hold for all the integer Renyi entropies and not for the von Neumann entropy? But these consequences, the interesting consequences only come from evaluating for the von Neumann entropy. And John and I did a lot of numerical, we tried to test this numerically in systems that were, I think, up to 5 by 5 qubits, and millions of examples, and we never found any violation. But strange things can happen. Yeah.
Okay, thanks very much. Yeah.
Mm-hmm.
Thank you very much. There's also a question by Peter. Please go ahead. You're muted.
Hi, yeah, thanks very much for the talk, Patrick. I'm just sort of trying to find connections to application here. So, for example, does your theory here on the reflected entropy shine any light on the sort of interior of black hole physics?
Does this one shine any light on the interior of black hole physics?
Yeah.
I don't. I'd have to think that one through.
Right.
So the geometries that we're looking at right here are all, in these cases where we're constructing these wormholes. These wormholes are non-traversable, and so you can think of them as being black hole geometries with multiple asymptotic regions. And so we are talking about the interiors of black holes. And so in that sense, they are present, but I don't know that it's saying anything specific, terribly novel about them. The larger story of it from qubit, I'd say has shown us some interesting things about the interiors of black holes. Like one example, people started thinking about what it would take to make so naturally in these situations where if you have a black hole geometry, which in ADS CFT corresponds to a thermal state of the CFT, the canonical purification is something called the thermofield double, and that's a two-sided wormhole. It's like that's the maximally like the geodesic completion of the original geometry. And so but those wormholes are non-traversable, right? Like two people could you could fall in from one side and someone could fall in from the other side, and these two different asymptotic spacetimes and meet in the middle, but you can't fall in and come out because you've fallen into a black hole. But by introducing some interactions between the left hand Hamilton, like the Hamiltonians associated to these two sides are non-interacting. Like strictly, there's a Hamiltonian for the A side and there's a Hamiltonian for the A star side. But by adding just the right kind of interaction between them, you can make the wormhole traversable.
Oh, I see.
And once the wormhole is traversable, you can send probes through. Right. And so you've modified the geometry by adding this little perturbation, but it's a very short, it only exists for a short period of time. And so you could hope that it doesn't change things too much. And then you say, well, I can actually think now of an experiment where I send a little probe into the interior and it comes out again, and then I can see what happens. And so that's something you could think about. And then there's the whole story I was discussing at the beginning about calculating the entropy of Hawking radiation, decoding Hawking radiation. All of that kind of stuff has been worked out at some level of detail, albeit a very abstract level of detail.
Oh, wow. So that's great. So it could be applied to that as well, calculating the black hole evaporation.
Oh yeah. So that was that I'd say was like the highlight of this whole intellectual development. But it happened a couple of years ago, and I did not I did not do that. Like the person who really nailed that at the end was my PhD student, Jeff Pennington. So I could give a talk about his work, which would be very exciting, but I figured I should probably speak about something that I've done.
Thanks. But does it also say anything about the internal states, the number of internal states of a black hole?
Oh, the number of internal states. Yes. So actually, even just this Ryuta-Kiyanagi formula, is essentially counting internal states.
Yeah.
In the sense that, like the entropy of a black hole, the argument that it has this entropy and it's proportional to the area, that is essentially telling you that the number of internal states is given by e to the entropy. And the Ryu-Takinagi formula is the strict generalization of that formula. But one thing that's really interesting about all of this is that you might have thought that to understand black hole evaporation, to really nail down, like, is it unitary? How would you perform the error correction, et cetera, that you would need a microscopic theory of quantum gravity, because it's all about the microscopic degrees of freedom.
It is.
And moreover, the semi-classical theory, which is general relativity, tells you that there's this light cone, and it tells you there's a horizon of the black hole and nothing comes out. So you would think that you could never do this all semi-classically. And the remarkable thing that has happened is that using effective field theory, that's really semi-classical, we can calculate all of these things that we'd like to calculate, and we get the right answers. It's just you have to know how to do the semi-classical physics properly.
Right.
So that I think was a huge surprise. Like Hawking back in the 70s, like a mundane way of telling this story is that when Hawking did his calculations, there were saddles in the path integral that he wasn't aware of. And if he'd included those saddles, he would have gotten the right answer.
Wow.
Like that like at the end of it, like, there's this whole development that sort of got us to that point, but you could just, like ahistorically tell it that way.
Wow.
Yeah.
Brilliant. Okay, great. Thank you, Patrick.
Yeah, you're welcome.
Thank you very much. We're running out of time. I don't know if there's any quick final question. Otherwise, I actually have a question that I think we can discuss later. So because it's time and I see some people need to leave. So let us close the seminar now. Thank Patrick once again and announce the next session. So thanks again, Patrick, for this really fascinating talk.
Thank you again for the invitation.
And so the next seminar, we meet again in a month's time on the 9th of March. Saverio Pascazio from the University of Bari will tell us about the dimensional reduction of gauge theories and quantum simulations. So we look forward to that. And just to close, I would like to thank the organizers again. So the co-organizers, Andres, João, and Simone, who are here, as well as the local organizing team, Rafaela and Sagar, who are also here. So thank you very much to all. Thanks to all the participants, and special thanks to Patrick for joining. Thank you very much.
Thank you.